Okay, so in this week we're going to talk about multiplication and division of whole numbers, and I'm going to start with just their models. So I'm discussing sorts of one of the first part of sections 3.4 and 3.5. I decided to combine it this way. So let's talk about the multiplication of whole numbers first. So we define the multiplication n times a to be through this repeated addition, where we say, okay, n times a, right, is the same as a plus a plus a. So basically a added n times, right? And if n is 0, then we define 0 times a to be 0, right? So for example, so this is the definition of multiplication. So let's of whole numbers. So let's say 3 times 4 will mean that 4 has to be added, right, 3 times, and that means 12. Okay. So this your n here is 3, and your a here is 4. So 3 times 4 means 4 added 3 times. Now, when you will be showing this property of this definition of multiplication using models, then one that is most intuitive, the one that demonstrates this repeated addition approach, is through blocks or through number lines or sometimes sets. I'm going to explain that in a second, but let's go through at blocks first. So say I want to demonstrate what is 5 times 4. So I know it's 4 plus 4 plus 4 plus 4 plus 4, basically 4 added 5 times. So it's like aligning blocks of length 4, 5 of them, right, in a row. So I have 5 blocks of 4. So when I add their total length, right, I'm going to end up with 20. Okay. And the kids would like find matching blocks. So 2 blocks of 10 would match the length of 5 blocks of 4, both amounting to 20, right, length. Say 20 inches, whatever is the unit of the blocks here used. Okay, the same repeated addition kind of could be given through like a number line, because the blocks is really, if you were to draw it, you would probably represent it with the number line, which means that I'm moving by 4 5 times, right? Because I want to add 4 5 times. So it's like saying I move 4, from 0 to 4, another 4, another 4, another 4, another 4, which gives me 5 fours, and so I end up at 20, right? And sometimes we also can represent it as 5 sets of 4. So for example, let's say I have 4 dots or some kind of objects, and I want to have 5 sets of those. Okay. So combined, I would end up with 5 sets of 4. So combined, I have 20 dots, or whatever, 20 apples, whatever you're combining in each set, right? Okay. Now, so that's kind of is repeated addition. So that's a model representing the definition of a multiplication as a repeated addition, which again could be represented through blocks, through number line, or maybe sets. Now, another way to represent a multiplication using a model is an array model or area model. So array model is, or let's start with area model, that's maybe more intuitive. So if I want to represent 5 times 4, then I can create a rectangle 5 by 4. So the length is 5, the height or the width is 4. So I have here total number, the area is of this is 20, right? And you can also, not always, but you can split it into like 5 squares, right? And the width is 4 squares, so combined you can also count how many squares you have, and this would be 20. Okay, but the area is 5 times 4, it's 20 for this rectangle. Now, array model is similar. You put here, you have 5 rows and or here's 5 columns with 4 rows, right? And then the number of dots you will count, right, would be 20, right? So again, I have here 5 columns and 4 rows. We will learn later that multiplication is so-called commutative, meaning that really order doesn't matter, because 4 times 5 is the same as 5 times 4, but let's wait with that. So technically you can arrange this area or array the other way around. You can make 5 rows and 4 columns. It still would represent the same multiplication. And the last model is so-called Cartesian product model. So I'll remind you that, remember, Cartesian product is just a set that gathers ordered pairs where the first component belongs to set A, the second belongs to set B. And when we count the number of elements in the Cartesian product, so number of ordered pairs, then it's always the same as the number of elements in the set A times the number of elements in the same set B. Let me give you an example. So suppose you can order a soy burger on a light or dark bread with one condiment, mustard, mayonnaise, or horseradish. So let's think how many different combination of orders the waiter would see, right? So we know that people can order dark or light bread, and with each option there also is an option for a mustard, mayonnaise, or horseradish. So waiter would see dark with mustard, or dark with mayonnaise, or dark with horseradish, and the same for light, right? Light mustard, light mayo, and light horseradish. So you can write it as a such diagram, right, where you have dark and light. That was options for bread, and then for condiments, mustard, mayonnaise, or horseradish. But that's really, this diagram is really representation of a Cartesian product. So one of the sets, I called it B because that's bread. It's light or dark. And then condiment, C set, contains options mustard, mayonnaise, and horseradish. So now let's pair them. So you can have light bread with mustard. So we have this ordered pair, light mustard. You can have light with mayo. You can have light with horseradish. And then you can have dark with mustard, dark with mayo, or dark with horseradish, right? So that's a Cartesian product of B with C. And if you count now total number of options, would be 6. 2, which is the number of options for bread, and times 3, which is the number of options for the condiment. So that's a Cartesian product model, and you're going to see how it is implemented more on the next example. So the following problems can be solved using the models shown for multiplication. Work through each problem using the suggested model. So let's start with repeated addition. So one piece of gum costs $5. Or $5, it would be a lot, but let's say it costs I guess $5. How much do 3 pieces cost, or 5 cents? One piece of gum costs 5 cents. How much do 3 pieces cost? So 3 pieces, right? That means one piece is 5, another piece is 5, and the third piece is 5 as well. So that would be 15. So here the problem was 3 times 5. 3 gums, each worth $5, right? So if we use repeated addition model to represent the cost of 3 gums, each costing $5, then we would say 5 plus 5 plus 5, because every time I pay 5 cents, right? So not dollar cents. Okay, let's use number line for the next one. If Al walks 5 miles for 3 hours, how far has he walked? Okay, so I can represent that on the number line. So here's 0. Let's say here is 5. Let's say here is 10. And let's say here is 15. So Al walks first hour, right? It walks 5 miles for 3 hours. So basically in the first hour, he walked 5 miles, right? Then another hour, he walked again 5 miles. And then another hour, he walked again. So that's the third hour, he walked again 5 miles. So combined, he walked 15 miles. Okay. So notice we, in each of this problem, those two problems, we represented 3 times 5 because he walked 5 miles for 3 hours, right? So it's 3 times 5. This is the distance. Array model. A sheet of stamps has 4 rows of 5 stamps, okay? How many stamps are there in a sheet? So we have 4 rows. So I'm gonna draw a line, but I know we're gonna place stamps there. So we have 4 rows of 5, 1, 2, 3, 4, and 5. Let me just, maybe this is a little bit too close. 4 and 5. So on each of this here intersection, right, there is a stamp. So we have 4 rows with 5 columns of stamps, right? So this represents 5 times 4, which is 20, right? We have 20 stamps. So 5 columns of 4 rows, or 4 times 5, either way is fine. Area. If a carpet is 5 feet by 3 feet, what is the area of the carpet? So we have 5 feet by 3 feet. Okay. That's your carpet. Okay. So what's the area of this carpet? Well, it's 5 times 3 or 3 times 5, either way is the same thing, which is 15 square feet, right? Not that units are not that important here, but just to demonstrate that the area is 5 times 3. And finally, the Cartesian product model. Al has 5 shirts and 3 pairs of pants. How many different shared pants combinations are possible? So we have 5 shirts. So let's say we have a set of shirts. I'm going to call it shirt 1, shirt 2, shirt 3, and shirt 4, shirt 5. And we have a set of pants. First pair of pants, second and third. So how many different shirt pants combination I have is a Cartesian product, is the set of ordered pairs. So I could put shirt 1 with pants 1, or shared 1 with the second pants, or shared 1 with the third pair of pants. He can do the same thing for shirt 2, shirt 2 with pants 2, and shirt 2 with the third pair of pants. The same for shirt 3, same for shirt 4, And the same with the fifth shirt. Can pair it with the first pair of pants, the second, and the third. Right, it's all, I couldn't fit it in one line, but it's all like ordered pairs separated with by comma. And we know that the number of shirt pants combinations is the same as the number of shirts times the number of pants. So it's 5 times 3, or total number of shirt pants combination would be 15. Okay, so that's the Cartesian product representing 5 times 3. Okay, so let's look at the properties of whole number multiplication. So first property is the closure. So when we take two whole numbers, when you multiply them, it's another whole number. So we're not going to get any negative number or anything if we have two whole numbers. Remember, whole numbers are 0, 1, 2, 3, 4, and so on. So whenever you multiply any two whole numbers, you're still within the set of whole numbers. Now, commutative property, I mentioned that earlier, the order really doesn't matter. The same property we had for addition, right? A plus B was the same as B plus A. So same as for multiplication. And let's show this using the area model. So whether I calculate what's the area of rectangle 5 by 3, or here 3 by 5, meaning if I put the bottom dimension is 3 and this is the height is 5, is the same as if the height is 3 and the length is 5. Both of those rectangles areas are 15, right? So this shows that 5 times 3 is the same as 3 times 5, okay? Okay, let's look at the associative property of multiplication. That we had the same, I remind you that just to connect the dots, we had the same for addition, right? When we added, we were able to move the parentheses one to the left, or group pair one over, because it didn't really matter which pair we added first, as long as we just added like the neighboring terms. So I could have added A with B or B with C first. Same thing is for multiplication. So I can first multiply, if I have three numbers, I can first multiply A with B and then C, or I can first multiply B with C and then A, right? In fact, if you combine commutative and associative property, then one can show that we can actually also multiply A with C and then with B, because we can switch the order and group appropriately, but that's for another question. So how to demonstrate this associative property? Let's look at what's left hand side. It's A times B times C. So for example, let's look at the problem 3 times 5 times 4. And we want to show it's the same as if I multiply 3 times 5 first and then by 4. So notice here that I'm proving that 3 times 5 times 4 is the same as 3 times 5 and then by 4. So 3 times 5 by 4, I draw 5 by 4s. So those are rectangles. And I have 3 of those, right? So notice I have 3 rectangles 5 by 4. Okay, so how about how to demonstrate 3 times 5 times 4, where now I have a rectangle 3 by 5, 4 of those, right? 4 times. Okay. Now notice that now if you were to construct a cube out of it, right? Then in either case you would end up with a cube that's has dimensions 3 by 5 by 4. So you would end up with the same cube. Okay. And then we have also identity property of multiplication, that is anything multiplied by 1 is A. 1 is this so-called multiplicative identity. because when it kind of partakes in multiplication, it doesn't change the number, so it's still a. So a times 1 is a, and 1 times a is a, right? Because again, its multiplication is commutative, so it doesn't matter from which side you multiply by 1. And then we have zero multiplication property, that multiplication by 0 is 0. And it again doesn't matter, since multiplication is commutative, whether you multiply by 0 on the right side or on the left side, either case, they produce 0. And finally, the last one is, or the last two, which are kind of the same, distributive property of multiplication over addition. So a times b plus c, you can distribute as a times b plus a times c. Notice the illustration, how we would represent a times b plus c. B plus c, right? So for example, in this case, we would do 5 times 3 plus 4. So 5 is the height of the rectangle, 3 plus 4. So is the length, is the here the width, right? So basically, this dimension is 3 plus 4. So I have 3 and then another 4, right, squares that forms this dimension. And then 5 squares on top form the height of this rectangle. So this represents 5 times 3 plus 4. So this is this rectangle. But now if you do separate 5 times 3, then there is rectangle whose height is 5, but the width is 3. And this is the rectangle whose height is 5 and the width is 4. So notice that those still represent the same area, because it's kind of like the original rectangle split, right? But they, if you count the area of the original rectangle, the big one, this one, is the same as the sum of areas of those smaller rectangles, because they kind of came off of the big rectangles, right? So that's kind of illustration for this. And then you have distributive property of multiplication over subtraction for whole numbers. Here we assume that b is bigger than c, so b minus c is still a whole number. Remember, we want to, that we're learning about models of multiplication on whole numbers, so that means we don't want to produce anything negative, right? We want to stay within 0, 1, 2, 3, 4, 5, and so on. That's why here we assume b is more than c or equal than c. And you have the same distributive property. Okay, let's play around a little bit with those models and show some other properties we can derive. So use an area model to demonstrate that x plus y times z plus w is the same as this: x plus times z plus x times w plus y times z plus y times w. A lot of us probably see what happened algebraically. We call it that we foiled it, because we kind of used first, outer, inner, and last kind of model where we distributed it. But remember, we operate here only on the, right now we want to demonstrate it using an area model. So I draw the height of my rectangle will be x plus y. So I have, this would be x, and then I will need another y. Let's say it's something like longer. This is y. So that's the, that would be the height of the rectangle. And the width is w, sorry, z, and then plus w. That's really the same, but I'm gonna do it here, z, and this one is w and z. So I have the rectangle, the left hand side, right? I can demonstrate this left hand side is a rectangle whose here height is x plus y and the width is z plus w. But then we know we can partition it into 4 rectangles, this one being x times z, this one being y times z, this one has height x but width w, and this one has height y and width w. Okay, so this shows that basically this thing, right? It shows that the area of the rectangle whose height is x plus y and the width is z plus w is the same as sum of areas of those four rectangles, xz, xw, yz, and yw. Okay, now let's prove the same using distributive property. So I want to show that x plus y times z plus w will be equal to this. So I start with the left hand side, right, with this. And what I will do, I will use I can only use the properties of my multiplication that were stated here. So I'm going to use this distributive property of multiplication over addition. So if you have one number a, you can distribute it over this multiplication over addition. But the problem here that one can kind of have is that this is not one number, it's x plus y, but I'm going to think of it as one number. It's in the parentheses. So I'm going to think, oh, that will produce some number. That I think of it as 1. And that will be using distributive property. So by distributive property, I can distribute, this is like one number. I can multiply z, and then it can be distributed over addition and multiply w. Okay. Then let's look back at this. I'm just going to use one property, the distributive property of multiplication over addition, which tells me if I have this number a in front, it can be distributed over addition, right? Okay, so I look back and say, okay, I want to distribute this thing even more, now z over the addition, but technically in this property, z should stand in front. So I'm going to use now commutative property of multiplication that allows me to change the order in the multiplication. So z can be in front, and the same here with w, right? So that's the commutative property of multiplication because I flipped the order here. And then I'm going to use distributive property of multiplication over addition again. So now using distributive property of multiplication over addition, I'm going to use z times y, and here the same for w. I'm using distributive property of multiplication over addition. And I look, is this what I wanted to say? I wanted to have term xz, xw, yz, and yw. Notice that all of them are kind of reversed. I wanted to have xz. Well, that's not a problem. Now again, I can use commutative property and reverse that. So I can take xz, yz, reverse xw, and yw, right? And that now I arrived exactly at the right hand side. So what I did, I just used the property listed there. Let's see, we're inexperienced. We have no idea how the multiplication, how those multiplication property work. So I slowly thought of x plus y as like one number. So I distributed that over addition, and according to that property, to distribute the multiplication over addition, that number should stand in front. But in fact, I know I have commutative property, so if it was behind, that I could distribute it too. But sticking with those rules, I distributed, and then again I flip the order so that number is in front. I distributed again, and then I had to at the end flip the order of all the terms. Okay, let's look at number 3. Determine whether the following sets are closed under multiplication. So what basically it says here that, let's start with A. If I have the set 0, 1, and if I perform all multiplications, so what I can multiply, 0 with 0 with itself, 1 with itself, 0 with 1, okay? And notice that I'm back, I'm still within the given set. All those possible multiplications only produced values 0 and 1, which are within the kind of permitted values, right? Because to check whether it's closed, I need to make sure that all the products, all the multiplication values of multiplications will stay within the set. So in this case, it should be either 0 or 1. So yes, this set is closed with respect under multiplication. Let's look at B. 1, 4, 7, I'm going to rewrite it. 13 and so on. So that's a arithmetic sequence, terms of arithmetic sequence. It increases by 3, right? So let's see. Okay. So that's a tricky question because there's so many, I cannot list all possible multiplications, right? But I can for sure at first I can test it, okay? What if I took, say 4 times 7? That's going to be 28. Will I have 28 there? Well, let's list a few more terms. So remember it increases by 3, right? So keep adding 3. And yes, I will stumble upon 28. So actually, it will be still within the given set. What about, one can wonder, what about 4 times 10? Well, 40 will be in this set. Well, you would have to keep adding 3 and you would encounter 40 along the way. Okay, but that doesn't it's not very convincing. One can say, okay, you just tried few numbers and the result always turned out to be in the set, but it's not a kind of guarantee that any other pair that you multiply will result in something that's back in the set. So what we should do? Well, let's approach it mathematically. So remember, this is arithmetic sequence. So to get the formula for the arithmetic sequence, I need the A1, which is 1, and I need the difference, and the difference is 3, right? Because to move along the terms, I need to keep adding 3. And so I can come up with the formula for this, for the terms in the set is 3n minus 2. So that's the formula, okay? So the question is, if I have arbitrary two elements from the set, let's call one of them will be 3n1 minus 2, right? Because basically maybe one more time. What I discovered that any element from the set is of the form 3n minus 2, where n is some natural number. For example, 13, right? I can write as 3 times 5 minus 2. So that 13 would be, n corresponds to n equal 5. And sure enough, it's the fifth term of this, it's a fifth, right? It's the fifth term of this sequence, right? For example, 25 corresponds to n equal 9 because 25 is 3 times 9 minus 2, right? That's 27 minus 2, 25. So that's a 9. So basically, any term in this sequence can be written in the form 3n minus 2, where n is some number, right? So let's multiply an1 with some other term an2. So for example, an1, let's say n1 is 10. So the 10th term of this sequence, I multiply with an2. Let's say n2 is 2 with the second term of the sequence, right? But I want to keep it as arbitrary as possible, so I then can prove that it happens in full generality, right? So basically each term is of the form 3n1 minus 2, and the other is just 3n2 minus 2. So n1 is some natural number, and 2 is some other natural number. So now when you perform this multiplication, right, like to use distributive law, so this times this, that's 9 n1 times n2. This is 6 n1, my mistake. then this would be 6 and 2, and this would be plus 4, right? Okay, so is it of this, so it for this to be still back in the set, right, it has to be of this form, 3 times n minus 2 for some n. So what I will do, out of those, I will write, okay, so I want to create minus 2, so I'm gonna, at the end, I'm gonna add and subtract 2. So notice I add and subtract 2, because first thing I'm creating this minus 2, right? But I cannot just create minus 2, I have to counteract it with positive 2, because then that means I haven't really changed anything. So combined, I'm looking now that I have 9 and 1 and 2, minus 6 and 1, minus 6 and 2, plus 6 minus 2, right? It's still the same as plus 4. But then out of those terms, I'm going to factor out 3. And then at the end, I factored 3 out of all those terms, which means now and one can wonder, this is another question, this is a natural number, right? So think of it, let's call this entire thing some capital N. So this is of the form 3 times n minus 2, which means this product belongs back to this set, okay? So this was like official proof, but let's say you could also observe it. I'm not expecting you to prove it, but just let's hope you would be able to observe that when you multiply any two elements of the set, you're back in the set. Okay. And I'm gonna skip C. I'm gonna look at this will be close. I want you to check it. I'm not gonna prove it, but just look at it. 2 times 4 would be 8, which is you're back in the set. 4 times 6 would be 24, and you won't see it because this is a geometric sequence, by the way, so you have to keep multiplying by 2, right? So let's see, maybe it's not gonna be. So keep multiplying. No, sorry, it's still arithmetic. So keep it's not geometric, it's actually keep adding 2, right, to move along the terms, so it's still arithmetic. So if you multiply 2 terms of the arithmetic sequence, you're actually back in the, it ends up being a term of the same sequence. So I already confirmed that, say, 2 times 4 is 8, which is in the set. But what about, say, 4 times 6 is 24? Will you get 24? Well, you won't see it until you kind of keep adding, right, 2 until you arrive at 24, and you will say yes, right? Different way to look at this is actually maybe even easier, is that if you 2, 4, 6, 8, 10, what do they represent? Even numbers, right? So those are even numbers. And when you multiply 2 even numbers, the result is an even number as well. Say 2 times 10, 20, 4 times 8, 32. The product of 2 even numbers is an even number. So yes, it's close with respect to multiplication. And how about C? Two and 5, that's a set. You have a set that contains 2 and 5. And immediately I see, if I take 2 times 5, that's going to be 10, and 10 is not part of the set, so this set is not closed under multiplication. So basically what it means to be closed, remember what it means is that when you multiply any two elements from this set, the result has to be in the set as well. And 2 times 5 is 10, and 10 is not part of this set. This set contains only two numbers, 2 and 5. So not closed under multiplication. Okay, which property is illustrated in each of the following? Let's look. 6 times 5 times 4 is the same as 6 times 5 times 4. So that's what? Associative. Whenever you just move parentheses one to the left or one to the right, depending from which side you're looking at it, so you're grouping it, you move this grouping one to the pair 1 over, then that's associative. Okay, now let's see this one. Notice grouping didn't change, still on both sides 5 and 4 are grouped together and they're enclosed within parentheses, but what changed was the order. Instead of 5 times 4 on the right side is 4 times 5. Changing order means commutative property. Now let's look at C. So let's see about the grouping stayed the same, right? 5 is still grouped with 4 on each side of the parentheses, so that's not going to be associative because grouping remains the same, but the order changed. What changed? 6 switched, right? Instead of being in front of 5 times 4, is now behind the 5 times 4, which again means commutative. Now here, whenever which property says that when you multiply by 1, it doesn't change the number. So 1 times 5 times 4 is just 5 times 4. It's the identity property of multiplication, right? So this was this one, that multiplication by 1 doesn't change the output, right? So basically 1 times A is A. That's identity property of multiplication. This is zero. Let me make sure that I call it same as in the book. Zero multiplication property. So zero property of the multiplication. Basically that says that multiplication by 0 is 0. And well, what about this one? This one is we grab 3 times 4 right here, and we distributed it, first multiplied by 5 and then multiply 6 by it. So this is distributive property of multiplication over addition, right? Distributive property. Okay, let's look at this. What multiplication is suggested by the following models? So here I have 1, 2, 3, 4. 4 sets of 3, right? So this is 4 times 3. It's like 3 being repeated 4 times, right? So it's kind of like repeated addition of 3. 3, 3, 3, 3, which represents 12. And here this is, again, height is 3. And width, let's count, 1, 2, 3, 4, 5, 6, 7. So this is a 3 by 7 rectangle. So this represents multiplication 3 times 7, which is, we can count to be 21. Show that a plus b squared is a squared plus 2ab plus b squared. By the way, this is something that a lot of us make mistake, and a lot of students make mistakes, assuming that a plus b squared is the same as a squared plus b squared. And this is far from truth, because there is, when you think of a plus b squared, you really have to multiply a plus b with a plus b. And we're going to do it actually in part A. So let's let's do that. The distributive property, so show that this is true using the distributive property of multiplication over addition and other properties. So basically what I'm going to do is when I'm proving something algebraically, I always start with one side and the goal is to arrive at the other side. So I'm going to start with the left-hand side. I understand first what the square stands for. And then I use distributive property of multiplication over addition. So I think of this as one number and I'm going to distribute it, right? So first, distributive property of multiplication over addition will allow me to do this, right? Then technically I will distribute again, but technically in this distributive property, to this thing I want to distribute over addition should be in front. So I can use the commutative property now to switch the order, right? So that A would be in front in the multiplication and here B would be in front. Now I'm going to apply distributive property of multiplication over addition. A times A plus A times B. Here times B times A and B times B. Now again, B times A and A times B are the same things, so I can use commutative property and also the fact that A times A is A squared. To here switch B times A into A times B, which gives me two terms of AB. And gives me what I wanted to have, right? So I have it. Now let's use an area model. So I want to demonstrate A plus B is this so basically A plus B squared. So A plus B times A plus B, this one, I draw as a rectangle whose height is A plus B and whose width is A plus B as well. So let's say this is A. This, let me mark in red. This is A. And let's see, this one would be B. This is B. So combined length here is A plus B, right? Same thing here. This would be A. And this one would be B. Okay, so this is again still A, and this is the same length B. So basically we're creating a square, right? Because both length and width, or height and width, are the same. So again, this is combined has the length of A plus B. So on one hand, this is a square whose area is, so area of the big square is A plus B times A plus B, or A plus B squared. But then the same area can be split into 4 squares. This one is the square A by A, so A squared. This one is A times by B. This one is B times A, which I know is the same as A times B. And this one is B times B, or the square B squared. So I see that it's the same as sum of areas of those smaller squares or rectangles comprising it. So would be 1 square A by A, then 2 rectangles A by B, and then 1 square B by B. Right. Okay, let's use this property. So let's use the fact that A plus B combined squared is A squared and B squared as outer terms, but in the middle you have 2AB. Okay, so use this property for 100 to calculate what's 101 squared. So I split 100 into the sum. I want to use this property, right? So again, I want to use the property that A plus B squared is a squared plus 2ab plus b squared. So first I needed to have a sum. So now this 100 is like my a, and 1 is like my b, right? So I need, according to that formula, it's going to be a squared, my a is 100. There's going to be 2 times a times b. My a is 100, my b is 1, plus 1 squared, right? So that's squaring at 10 or 100 just means doubling the number of zeros. This is 200, and this is 1. So that's 10,201, okay? And we have it. And notice it wasn't that difficult to compute, right? If we use this property, but if we wanted to, in our heads to kind of multiply 101 by 101, then it kind of seems more complicated. Okay. Okay, let's look at number 8. The product 6 times 14 can be found by using 6 times 10 plus 4. So again, I'm going to here use distributive property of multiplication over addition. But first we had to create addition. So we split 14 into more convenient 10 plus 4. So now I can multiply 6 by 10 and 6 by 4. Each multiplications are pretty easy, and then adding together create 84, which is the product of 6 times 14. That's, guys, how I do my kind of multiplication in my head. And what properties are used here? Well, distributive property of multiplication over addition, right? This is the property that was used here. Okay, so use this technique of mental compute to do the 32 times 12. So again, I want to use this distributive property over addition. So let's create the addition first. So 12 is 10 plus 2. So now we can distribute and do 32 times 10, and then 32 plus 32 times 2. Multiplication by 10 or 100 just means adding that zeros, right? And this is 64. So now when you add together is 384. And that's what 32 times 12 is. Finally, last two exercises, using the distributive property of multiplication over addition, we can factor as in x squared times xy is x, and in the parentheses x plus y. Use the distributive property and other multiplication properties to factor each of the following. Okay, so let's start with a. So I have x times y plus y squared. So first what I will write is y squared is y times y, right? Now I want to factor out y, but technically, to be very strict, I would like this y to be in front. So I'm going to use commutative property first and switch that into y times x, and this is y times y. So now this y here can be factored in front, and we have it. So this is using distributive, right, property of multiplication over addition. And I'm being very strict here because technically I want it to be all those things I'm factoring out to be on the left side. That's how distributive property of multiplication over addition was stated. But truly, since multiplication is commutative, it doesn't really matter. Let's look at the next one. So x times y, we have multiplication, but here there is no multiplication. And to factor out, I have to kind of reverse the distributive property of multiplication over addition. I have to have a multiplication. So here I can write x times 1, that's x. So what property did I use? Identity property. I remember 1 is like an identity. Okay, so now that allows me now to use distributive property of multiplication over addition, which claims that this is the same, right? X times, in the parentheses, y plus 1 would be the same as x times y plus x times 1. So two properties had to be used. First, identity property, replacing x with x times 1. And then distributive property. Let's look at the next one. So here I see, if you know probably from arithmetic or from algebra class you took, that AB could be factored out here. But I want to be showing it step by step. So first I'm going to split that into A times B, and this one A times B times B. Then I know I'm going to be factoring A times B, so let's switch the order here so that A times B is in front. But that first means commutative property. But I know I can do it, right? Okay. Which, by the way, to be very strict, I should first mark it as in the parentheses and then use associative property. So let's be very strict, because A times A squared is the same as A times A. So before I use commutative, let's use associative, which says, okay, I can pair A with B, and here A with B as well. Now let's move this AB in front. So I switch the order using commutative property. So A times B goes first, and here A times B, I like how it is in front. So now this A times B being in front, I will factor it out using distributive property of multiplication over addition. So now I'm left here with A, here with B. So that's distributive property of multiplication over addition, and I have it. So it's kind of like factoring out AB. And last thing, a new from about multiplication, we're going to move to division models in a minute. A new model of car is available in 4 exterior colors and 3 interior colors. Use a tree diagram and specific colors to show how many color schemes are possible for the car. So we have in the exterior, right, we have 4 colors. I'm going to call it color exterior 1, color exterior 2, color exterior 3, and color 4th color, right? Okay, and then each exterior color can come in 3 interior colors. So color interior 1, color interior 2, color interior 3, and the same for if car has, say, second color option for exterior, still same 3 option for interior, right, are possible. So let's do this. Okay. Color interior 1, color interior 2, color interior 3, and same for the last one. I need a little bit more room here. The 4th option for the exterior color also comes with same 3 possibilities for the interior color. So remember, this is Cartesian product because technically each of these options can be written as a pair. Exterior color 1 with interior color 1. This is exterior color 1 with interior color 2, right? This is exterior color 1 with interior color 3, and so on, right? So it's really, this diagram is like a Cartesian product, and we know that that means that we have how many schemes? 4 times 3, so 12 color schemes, because it's 4 exterior colors times 3 interior colors. That's how many kind of pairings we would have, right? How many ordered pairs we would have.